This should be the third and last video on the idea of complex integration. So here we look at Cauchy integral formula. In the two previous videos, we had considered contours and paths, and then later we saw Cauchy's theorem, which talks about the fact that for every analytic function, their integral along a closed path is actually zero. Okay, and here we look at Cauchy integral formula. Let's see that. So, a fundamental result in complex analysis that allows computation of function values using contour integrals is actually what a Cauchy integral formula is. And the statement of the Cauchy integral formula is this, that if f of z is analytic inside and on a simple closed contour C, and let A lie inside C, then we can say that f of A, the function evaluated at a particular point A, which lies inside the closed contour, is 1 over 2 pi I integral on the closed curve C of f of z over z minus a dz. So the interpretation here is that the value of an analytic function at a point depends only on its values along a surrounding contour. Okay, so analytic functions are highly constrained in that sense, and boundary information determines interior values. So the boundary tells us all we need to know about the circle, as about the function, about the analytic function as far as Cauchy integral formula is concerned. So we talk about the generalized Cauchy integral formula. For derivatives, we say that f of f n of a, that is the nth derivative of evaluated at point A, is actually n factorial over 2 pi I. So if it is fifth derivative, it will be 5 over 2 pi I. So nth derivative is n factorial over to be 5 factorial if it is f5, right? Fn is n factorial over 2 pi I integral along the curve C. So you have f of z all over z minus a raised power n plus 1 dz, like that. This is the generalized one here. So example one. So uh we evaluate integral of z squared over z minus 1 along the closed curve C, like that. So where C is the circle, C is the circle with radius 2, right? So the solution is f of z is z squared, which is analytic everywhere. So that is established. A is equal to 1, and it is inside C. How do we know it is 1? Because z minus a, z minus a, z minus 1. So 1 is a, as we already know. So, and with that in place, we can then use CIF, the Cauchy integral formula, to say that the integral of z squared over z minus 1 dz along the closed curve C is simply uh will simply be 2 pi I dot f of 1, like that. So 2 pi I dot f of 1, um, like that. So, and then of course, f of 1, f of z is z squared. So f of 1 will be 1 squared, which is simply 1. So then for the others, we have 2 pi I right here. So that's 2 pi I multiplied by this, and the answer is just 2 pi I. So that means it's somehow analogous to integrating 1 over z dz along a closed path, like that. So example two, which will help us with a bit more light. So evaluate along the closed curve C, e raised power z over z cubed dz. So f of z is e raised power z. Then a is 0 because there's nothing like, normally it should be like z minus something over raised power 3. But here we have z minus 0. So a is 0 and n is 2 because n is 2. What tells us n is 2? Hmm, let me see. N is 2. Okay, yeah. N is 2 because the power of z is 3. Because this 3 here means n plus 2 plus 1. So n is 2 in that sense. Because, I mean, that comes from, just refer to this general formula. So n is 2 in that regard because the power of z is 3. So using the formula, then we know that this is 2 pi I over 2 factorial. So it's like this one now, we transfer. So this integral now will be So you transfer this to the other side, that'll be 2 pi I over n factorial multiplied by the whatever derivative of the second derivative evaluated at a. So in essence, like what is basically happening here is this for easier understanding. So in case it may look like what exactly is happening, um, you know, if you have this function now, this is a general formula. So I'll just copy this and take it to the worksheet. So this is the generalized formula for the Cauchy integral formula, right? So normally, if you need this, usually the path we need. So if you need that path, it means you have to divide, you have to take this to the other side. And of course, when it gets to the other side, it reverses. So it means based on that now, integral along a closed path C of f of z all over z minus a raised power n plus 1 dz would simply be 2 pi I all over n factorial. That'll be 2 pi I all over n factorial multiplied by the nth derivative evaluated at a, basically. So this is another way to see it. So that's how to actually apply this formula. And that's exactly what's happening here. So in this case now, we now have 2 pi I. So here it was because here this is like raised to power 1. So n was 0. So we just evaluate the function at 1. But in this case now, this is n plus 1 is 3. So that means that n is actually 2. So if that is the case, then we have that we have 2 pi 1 over 2 factorial because n is 2. Then f prime prime evaluated at a, which is 0. So that means we differentiate f of z twice. So f of z is the value, the z under, right? So we have z cube. No, f of z is e raised power z actually. Yeah. So that's e raised power z. For the other one, it was just z squared. So f of z is the one at the top because that's what we have in the expression. F of z is the one at the top. So we have f of z is e raised power z. So from here now we have 2 pi over 2 factorial f prime prime of z evaluated at 0. So differentiate e raised power z f prime, that's e raised power z. Second time it's also e raised power z. So f prime prime evaluated at 0, that's e raised power z evaluated at 0, that's e raised power 0, which is 1. So in that case, we have 2 pi 1, 2 factorial is 2, and multiplied by 1, so 2 cancels 2. So the result of that is actually pi I, actually, like that. So we can talk about numerical verification using Python. So we want to approximate integral along the closed curve C for z squared over z minus 1 dz. We got that it was 2 pi I based on our computation here. So we want to use Python to verify the same. So here now, let's perform the numerical integration for the first example where f of z is z squared and the contour C is the circle with radius 2. The analytical result is 2 pi r. So we compare the numerical approximation to this exact value. So we define t from 0 to 2 pi and z is 2 e raised power it. And then we have the t to be t1 minus t0 and the z is what we got the other time. So if you put all of that together and we run it, we get that this is more or less like the numerical thing. So the real part is 0 because this is all these 10 raised power 10 raised power minus 16. So it's as good as 0. But on the other hand, we have 6.2 something something, which is actually close to the 2 pi I we got. So J now is our I. So 2 pi is roughly 6.288. Pi is 3.41 blah blah. So multiply by 2, you get 6 point. So you get 6.288 and all that. So the analytical result shows that we have 2 pi I because this first part is as good as 0. And the difference between this and the analytical result, between what we got here is just about decimal. So that's 0.005 and all that. So they are pretty close, the numerical and the analytical. So in essence, the Cauchy integral formula gives that f of a equals 1 over 2 pi I multiplied by the integral of f of z over z dz along a closed path C. So the key idea is that function values inside the region can be computed using only boundary values. So you can compute a function, the values of a function inside by using just the boundary values. And that's why we focus on the function f of z, the a, and the number of derivatives or something, the number or n. So this principle appears in physics and engineering. Then we can talk about Cauchy estimates. Now, if f of z is if the absolute value of f of z is less than or equal to m on a circle of radius r, then the absolute value of the nth derivative evaluated at a is always less than or equal to n factorial multiplied by m, that's that boundary, all over radius raised to power that nth derivative we have like that. Then we have that leads us to the Liouville's theorem that which tells us that if a function is entire, that is, it is analytic everywhere. The 20th video is on entire functions, which talks about everywhere analyticity. And if a function is entire and bounded, then it must be constant. I think we saw that at that point too. Then we go ahead to talk about maximum modulus principle, which tells us that an analytic function cannot attain its maximum value inside a domain. So the maximum occurs on the boundary. Makes sense. Then we talk about the mean value property, which tells us that f of a equals 1 over 2 pi integral from 0 to 2 pi f of a plus r e raised by I theta d theta. So the value at the center equals the average value on a circle. So the value at the center equals the average value on a circle. I think we've seen things close to this before also, which talks about the fact that every point is an average of surrounding points, that kind of idea. So that's like the mean value property. And then we have the identity theorem. So if two analytic functions agree on a set with an accumulation point, then they're identical everywhere. So we see example 3 in that regard. So for here, we want to evaluate integral along the closed curve C for sine z over z minus pi squared dz. First of all, the function f of z is sine z, a is pi, z minus a is pi, and n is 1 because 2 here means n plus 1. So if n plus 1 is 2, then n is 1. So what do we then do? We just have 2 pi I over, since n is 1, we just have 2 pi I over 1 factorial, which is 1 already. And then because n is 1, we have 1, we differentiate only once, and we evaluate pi at pi. So it means that about f prime of z, if you differentiate sine z, you get cos z. F prime of pi, that's cos z. When z is pi, we have minus 1. In that case, we just have 2 pi I times minus 1. That's minus 2 pi I. And that makes it easy. Normally, if you had to integrate this kind of expression, uh, you know, it is going to be a very long thing, right? But using the Cauchy integral formula, it makes very simple. It goes very easily because you can estimate the values inside the circle using the points on the boundary of the circle. Just identify f of z, identify a, identify n, and you get going. So in summary, a Cauchy integral formula links integrals and function values. Then it provides a method to compute derivatives using integrals, and it leads to major results like infinite differentiability, Liouville's theorem, maximum modulus principle, identity theorem. It is one of the central results in complex analysis. So the Cauchy integral formula is pretty useful, and it is one of the key things that complex analysis gave us. So we've come to that point where we talk about practice problems. So you already know what to do, but I'm going to solve two for you for sure. Um, so we have 1 to 20 as usual. So you have 1 to 5 here. Then you have 6 to 10, 11 to 6 to can we see, okay, 11 to 15, and then 16 to the end, 16 to 20. So I'm going to answer two of this. So I'm going to be answering 3 and 7. I'll answer 3 and 7, and then we'll call it a date with this one. So question 3 talks about evaluating the integral of e raised power z over z minus 1 dz, where c is the absolute value of z minus 1 equals 1, like that. So this is a circle whose center is not at the origin, but the radius is 1. Then the other one is question 7. Question 7 is e raised by z minus 1 squared dz. So let's go for that and see how it all goes. So don't forget, this is the general formula, and it's always helpful if all you have learned today is this formula, you are good to go because it can help you to integrate the most complex for expressions as far as you can easily identify f of z, identify n, and then identify a. With all of that alone, all you just need is you now fix up that here. So 2 pi I n factorial fn, that's if n is 5, you differentiate 5 times, and then whatever you get to evaluate at the a you have identified here. So those become the most important things you need to know there. So let's talk about problem 7 now. Problem 7. So problem 7, you need to evaluate in the integral along the closed curve c of e raised by z over z minus 1, z minus 1 squared. So dz, where c is absolute value of z minus 1 equals to, so let's go. Step 1. Step 1, identify the formula. Identify the formula. And I just showed you that the formula is integral along the closed curve c of f of z all over z minus a raised by n plus 1 dz uh, plus 1 dz is actually 2 pi I all over n factorial, the nth derivative of the function evaluated at a. That's important. So once you identify the formula, the next thing is to identify components. Step 2, identify components. Identify components. So here now, so this is what we have. F of z, that's f of z at the top there. So you see f of z is equal to e raised by z. Established. Next thing is a. Z minus a, right? Here, what do we have? We have z minus 1. So it means that a is equal to 1. So a is equal to 1. Then for the power, right? For the power, we know that the power here is n plus 1. So we have n plus 1 to be 2. So that tells us that n plus 1 is equal to 2. That implies that n is equal to 2 minus 1, which means that n is equal to 1. So we have f of z to be e raised by z, and we have a to be 1, and n is also 1. So with all of that in place, we can then compute in step 3. So step 3 now, we compute derivative. Compute derivative. So that tells us that, of course, we know f of z is e raised by z. That means that f prime of z is also e raised by z. Done. Then we need to evaluate that. Okay, yeah, based on what we have identified, right? We need to get all this together. Yeah, we need the first derivative because n is 1. Then n is 1 factorial is already 1. So we have this. So that means that f prime of z, that's f prime of a, which is 1, is actually e raised by z. That's e raised by 1, and that is actually e. So f prime of 1 is equal to e. That's a key thing we need to pay attention to. So having computed derivative, we can then go for step 4 where we apply the formula. Step 4, apply formula. Apply formula. So in applying the formula, we know that's integral from integral along the closed path c e raised by z over z minus 1 squared dz is equal to 2 pi I all over 1 factorial. That's because n is 1 now. Sorry, n is 1 here because 2 is n plus 1. Then f prime of 1. Okay, because that's we have the nth derivative of f evaluated at a. So this is our a now. So we just tidy that up. So 2 pi 1, 2 pi I, 1 factorial is 1. F prime of I is F prime evaluated at 1 is E. So we then have, for me, I like to write I 2 pi E. And that is the result right there. So the final answer is I 2 pi E in that regard. And that's problem 3, I think. Problem 7. No, problem 3. This is for problem 3, right? This is the first problem here. Um, okay, I'm answering questions 3 and 7. Okay, this is 2 pi I. This is problem 3 done. Okay, 2 pi I, 2 I pi 2 I 2 pi E. Okay, that's problem 3. Now we go for problem 7. Problem 7. So problem 7, want to evaluate integral along the closed curve C e raised power z over z minus 1 all squared dz, where C is absolute value of z minus 1 equals 2. So what do we do? First thing, you identify the formula as usual. So step 1, identify. My one can be very funny. Step 1, identify the formula. So by now, it should be part of us that this is integral along the closed curve C, f of z over z minus a raised to power n plus 1 dz equals 2 pi I all over n factorial nth derivative of f evaluated at a. So that's the first step. The second step now, step 2, we identify the components. Identify components. Identify components. So here we know that f of z is, so looking at the formula, f of z is at the top. So our f of z remains e raised power z here. So we have e raised power z. Then next, we need a. A, so z minus a. So we come here, z minus 1. Okay, that's also, so we have z equal, so we have a equals 1. Yeah, a is equal to 1. So you discover that it looks like there's always a connection between this z minus 1 and this z minus 1 here. I think the same applies to this place. So you have, yeah, z minus 1 always goes like that, I think. So, so a is 1. And then for the power, so for the power, this is z minus a raised power n plus 1. So the power here is 2. So n plus 1 is equal to 2. That implies that n is equal to 2 minus 1. And that implies that n is equal to 1. So we have n minus 1. I mean, n equals 1. A equals 1. F of z is e raised power z. So what do we do in that situation then? For some weird reason, the results are basically the same. So, what did I do before? Uh, so we got our e raised by 1 here. That's e. Yeah. Then for this, what did I identify here? This is problem 7. Did I start with problem 7 first? Oh, I'm doing problem 7 the second time. Ah, okay. No wonder I saw it's like the same thing. Okay. We've done problem 7 already. Problem 3, I think I just mixed up everything. Okay. We've done 7. Let me just leave it that way and just go and do 7. Let me just do problem 3, sorry. Problem 3. They have the same results, so I think that was a bit of confusion there. So I should have started with problem 3, then go to 7. So but I was supposed to, so I just went to 7. So let's do 3. Yeah, let's do 3. So for problem 3, we want to evaluate integral along the closed curve C e raised power z over z minus 1 dz. Okay, so I mean, I won't go through all the stress again. I'll just tell you first, identify the formula, right? Um, okay, for this now we have C on the closed curve z minus 1 equals 1. So what do we do? So, from the formula, from the formula, integral on the closed curve C, f of z all over z minus a dz equals 2 pi I f 2 pi I. Well, I think I like to use the general thing, n plus 1, 2 pi I over n factorial, f of n evaluated at a, basically. So if we compare that, right, we see that f of z is equal to e raised power z right here. Then here now, this is raised to no power. This is like power 1. So that's like power 1, right? So it looks like n plus 1 is 1 in that case. So, but first z minus a, and here we have z minus 1. So it means that a is equal to 1, and n is equal to n plus 1, right? N plus 1 is equal to 1. That implies that n is equal to 1 minus 1. That means that n is equal to 0. So we have n is 0. This is a is 1, n is 0, a is 1, and f of z is e raised power z. So if that is the case, all we just need to do is to, so uh, so this tells us that the contour encloses z equals 1. That's why n is 0, right? So we apply the formula now. So we have integral from e raised power z over z minus 1 dz to be over the closed curve c to be 2 pi I all over 0 factorial. That's like our n now, because there's power 1 here, so that's 0 factorial. That's what n is like. And then we have no derivative, right? So that will be f evaluated at a here is 1. So, and we know f of z if f of z is e raised power z, then f of 1 is equal to, then f of 1, right, is equal to e raised power 1, which is equal to e. So both problems have the same result. So this is 2 pi I. 0 factorial is 1. F of 1 is actually e now. So this is also 2 pi I e. Or just if you like to do it like me, that's I 2 pi e. So problem 7 and problem 3 have the same result. So on this note, we come to the end of the two uh, practice problems. Don't forget to try your hands on the rest. So I take it back to that page where I flashed the questions at you. So don't forget, try your hands. Uh, you have questions 1 to 5 here. Okay, let me wait a bit. Questions 1 to 5, 1 to 5, then 6 to 10, then 11 to 15, then 16 to 20. Okay, try your hands and be sure you have a good grasp of all these things we have been talking about. So you see the Cauchy integral formula is very useful in this whole process. You want to really master it to break to easily solve some problems that would otherwise be on very daunting tasks. You want to be able to try that out and just deal with it. So let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel, I thank you very much for doing that. And if you have not subscribed, go ahead, subscribe, hit the notification bell also so you can always get alerted each time a new video is released. Having done that, you can become a member of this channel by clicking on join. That gives you special privileges like becoming a member of the once you're a member of the channel, right? You have special privileges like getting to see some videos first before others, or having some videos made exclusively for you. Okay. Um, you know, you can also request for PDF copies of my notes for your personal use. Apart from that, we can hang out together physically if you're in the same location at any point in time, or online to discuss whatever interests you on this channel. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.